In this example, we're asked to compute the rate of heat flow inward across a cylinder. So the cylinder is given by y squared plus z squared equals 6 on this interval from 0 to 4 in the x direction. So let's start by sketching the cylinder. And then we can talk about heat flow a little bit. So here's our three-dimensional coordinate system. And in this scenario, we have, this is a circular cylinder of radius root 6. So I'll draw a little circle here and move it over. So this will be our cross section of the cylinder in the YZ plane. And again, the idea is that this goes through this radius of root 6 in these two locations, but then the cylinder itself extends in the x direction parallel to the x-axis. So there's our cylinder, and now this cylinder is cut off in the x direction by this value 4 here, and so we can just kind of sketch our own little circle here, and the cylinder that we're going to be looking at is, it's just the surface of the cylinder, right? So the cylinder is just this region right here. Okay, so there's our cylinder, that's our surface S. We want to compute the rate of heat flow inward across the cylinder. So that means that at every point on this cylinder, I'm just going to resketch the cylinder over here. At every point on this cylinder, we want to represent this normal vector, okay, that points inward. We want the inward pointing normal vector. And that's especially true, so that's true at every point along the cylinder, but it's especially true on the circle itself. And so let's think about this circle in the YZ plane. So in the YZ plane, our circle, not such a beautiful circle anymore, can be parametrized, so each point of the circle can be parametrized by a vector function, r of theta, which is equal to, so this is in the x, y, z direction, so x could be whatever, it's not dependent on this circle here, but the y and the z are given by the square root of 6 cosine theta, if we just use polar coordinates here. And then the z-coordinate is given by square root of 6 times sine of theta. Okay, and so this vector points directly outward from the x-axis to the boundary of the cylinder. And the normal vector that points inward is going to be just the negative of this, right? So our nu of x and theta is just equal to negative r of x and theta. So I didn't represent this as a function of x, but it is, because x is a variable here. And so this is our normal vector that we want to add up. Okay, our surface itself is given by this parametric function r, and the domain for both of these, this domain D and our x theta domain, is just the x changes, as we were told up above. The x changes from 0 to 4, so I'll just put 4 right here. And theta changes from 0 to 2 pi, so 2 pi is bigger than 4. And so this domain is just a nice rectangular region. And we probably noticed that a lot of these domains the parameter domains end up being pretty nice, and that's one of the reasons for wanting to parameterize our problems, because we can then work in these nice rectangular or otherwise nice domains. Okay, now we need to think about the heat flow. So we have worked out a formula for our cylinder, and we have a formula for the normal vector as well. This, by the way, is not the unit normal vector, right? So we're going to work back in the parameter domain. So we're going to use nu, the normal vector nu, and not the normal vector n, not the unit one. But here we need to talk a little bit about heat and the theory of heat conduction. And we're not going to get too much into it. I'm just going to give you guys some formulas. But this formula right here represents the temperature. So this is the temperature of the surroundings of this cylinder. And the conductivity, this is a constant. So this constant depends on the material that we're working in. So maybe we're underwater, maybe we are just in air, maybe this is all happening in some cylindrical cross-section of a chunk of metal or rock or stone or ground or whatever. But this conductivity constant K will change depending on what the material is, and this constant is determined by experimental data in general. Okay, so for us, for this example, it's just 6.5. All we care about really from a mathematical point of view is that it's a constant. This temperature is, of course, a function, and so there is a theory, physical theory of heat flow, which says that the heat flow vector field, so the vector field which represents the heat flow, f of x, y, z, is given by minus k times the gradient vector field of the temperature function. So minus k times gradient of u. And so this is our vector field that we want to integrate up, and we're going to find the flux. Basically, the flux of this is the heat flow. Okay? And so for us, again, we have our number 6.5 for k, and we're going to have to compute the gradient of u. But I'm going to write down a formula for what we want to compute, and then we can actually do it. Okay? So we want to compute the heat flow is given by the flux across this surface, which is this face of the cylinder, of F dotted with ds, that's flux. Okay? We know what F is, we know what ds is in our parameter domain. So this is going to be computed as the integral of d, okay, over d I should say, of minus 6.5 times the gradient of u of r x theta. So we're going to plug in our parametric representation of the surface to get the points along this here, dotted with nu of x theta, integrated up with respect to area, dA. Okay, and so this is what we need to compute. We just need to work out the details of this thing here. All right, so let me just remind us what nu is. So nu of x theta is equal to minus our vector r. So this is going to be minus x in the first component, and then the other two components don't depend on x, so it's going to be minus root 6 cosine of theta minus root 6 sine of theta. So there's our normal vector there. And then we need to take the gradient of our vector function u, of our temperature function u, and get the vector field, right? Get the vector field, which is the gradient, and then plug in these corresponding coordinate functions. Okay? So the gradient of u, this is always du dx, du dy. We compute this in the xy coordinate system first, x, y, z. And so this is going to be, there were no x's in that formula. And then remember, the heat flow is 2y squared plus 2z squared. So that's just going to be 4y and then 4z. And when we plug in our components, remember this is minus r. We have to plug in r for this. So the y coordinate component is going to be, so there's a 0 still. This ends up being 4 square root of 6 times cosine of theta, and then 4 square root of 6 times sine of theta. And we need to dot these together. So we need to take the dot product of these. And then we'll have our function that we're going to integrate in our x theta rectangular plane. So gradient u dotted with nu, this is going to be 0. Okay, so 0 times x is 0. And then the rest of this is going to be negative. So that dot is not supposed to be there. This is going to be minus 4 times 6 times cosine squared theta, minus 4 times 6 times sine squared theta. And of course, this is minus 24 times cosine squared theta plus sine squared theta, which is just negative 24. Okay, so our integrand is constant, and now our flux is going to be a breeze to compute. So the the double integral over our surface of f dotted with ds, this is the heat flow, okay? This is going to be equal to negative 6.5 double integral over our domain d, parameter domain d, of negative 24 dA. All right, but this is just, we can take this out, right, and this is going to be equal to, so positive 156 times the double integral over d of dA, but this right here, this is just 156 times the area of, now we have to be a little bit careful here, this is the area of the region D in the parameter domain, and that's of course just 4 times 2 pi, so that's 8 pi. And so this is 156 times 8 pi, and that is 1248 pi. And so there's the heat flow across this cylinder in the inward oriented direction.